So thank you everyone for joining our introduction to Velocity webinar. We have actually had a change of speaker. So today we are very lucky to have Thomas Westerling Bowie, who is our Director of Scientific Strategy and Business Development, doing our presentation today instead of Sami Blom, our Application Manager. Just a few housekeeping points for the webinar. So the microphones of all of you will be muted, but if you do have any questions, you can send them at any point during the webinar, and then a selection of them will be addressed at the end. If we don't have the time to answer your question, not to worry, we will send you an email afterwards to make sure that we get you all the information that you might need. And if you do have any issues at any point during the webinar, you can either email us or just send a question through the control panel. So without further ado, I will hand over to Thomas to start off this webinar.
Thank you, Emma. Good morning to everybody if you happen to be in the US, and good afternoon if you are in Europe. All right. So it's a great pleasure to be with you today, this morning, afternoon, depending on where you're sitting. I'm going to be introducing Aiforia quite quickly, the basics of what our platform is all about and what we do as a company. And then I will go into highlighting some of the new features that were released and are now available as part of Aiforia Velocity. It's been a really great start of the year, and the end of last year we brought on quite a lot of new developments that we are quite exciting to share and be able to provide for all of you potential users out there. So Aiforia as a company, we are a company founded in Helsinki, Finland, and we also have operations here in Boston, actually Kendall Square in Cambridge. We are a pretty agile group of some of the best software coders and product managers and life science specialists from both medicine and biotech areas. And we have customers essentially all over the world. As part of our platform, we also have a rigorous quality management system. So we have a number of certifications and quality assurance programs in place, and most recently we have released in Europe only the platform with an IVD CE mark for actually reading slides digitally on our platform. So our concept is that we provide essentially everything that you need as a scientist or a pathologist. You will no longer be held hostage to the IT department or the computational or statistics department or the AI guru in your local organization or institution. You are actually now empowered to just take charge of your own research or your own samples. And you can actually, on your own, without any help from really anybody, except our knowledge base and help documents, train your own AI model that you then can deploy in the cloud. So you can use any samples from any scanner. Our users are pathologists, researchers, educators, and you can use any device. So I normally in my work, I work off both a Windows computer, a laptop, and a Mac, but you can essentially use whatever it is that you do your daily computer work. That's the device that we will use. We are completely deployed through a web interface. So you have absolutely no install, you have no IT purchases to take care of. And the best thing with being a cloud solution is that it does not matter where you happen to be in the world. You can do it at home from your vacation home. You can do it in air as long as you have in-flight Wi-Fi, or you can do it at work. You have now the liberty of actually taking the work with you wherever you go. So one of the reasons that we started with our software platform is that image analysis is a really hard thing for humans to do. it's very subjective, and we are limited in what we can do. So this is a liver tissue with Herovici stain, and traditionally when you score an area like this, you would score a small area just because the 10x objective is actually covering only a very small part of the section. So you can visualize only a small bit of it at a time, and you can only quantitate thoroughly small areas at the time, and that usually leads to you actually just pick a representative area, you hope that it's representative, that you're not biased, and then you give your best estimate. And so then when you start looking around, quite often we have lots of variability between different operators, and especially in estimating areas of lipids here, in this case in the liver, the variation is quite big, and the deviation from actual true ground truth is quite high. So with quantitative analysis, regardless of the method that is used for the quantitative analysis, you can actually get a full accounting for all of the features in the slide. And not only that, but you can actually get a distribution, and you can get other spatial metrics, etc. So quantitative analysis actually allows you to, at a glance, really judge the entire biopsy or the entire sample, and not only a small subset of it. So the drivers of digitalization in pathology, because of course this is the first step to be able to using these quantitative methods, is to move away from the glass slide. And especially in Europe, and also gradually starting in, especially in the research area in the US, we are seeing a huge growth of digitalization. And the reason is that there's a huge amount of data in a slide, but manual and visual usually methods, they discard large amounts of the data. And these are expensive specimens, and they're hard to produce, they're hard to procure, they might be rare, so it costs a lot of money, both in reagents and in human labor. So throwing away a large part of the slide and reducing it to a binary score is quite detrimental to many organizations' mission, where they are, especially in the field of precision medicine and tumor heterogeneity, where you really need to capture the destiny and state of every cell on the slide. It's really important to move away from the subjective and manual read. And of course, we have the variability between different humans, so that you cannot compare between all humans necessarily that are doing the read. And then of course we have the lack of resources, more samples, less workforce. Drug research and development is more expensive than we really can tolerate, and healthcare delivery is also more expensive than the society can tolerate at the moment. So we need to make things more efficient. And here, of course, digitalization, automatic quantitative pathology, and AI comes in. So deep learning applications, I'm sure that you all know quite a bit about this. There's a lot of things that can be done with different neural networks. You can do false paintings. So basically, on the right-hand side, if you take a photograph and you tell the neural network to kind of apply famous paintings or the schemes of famous paintings to those photographs, they can actually make a pseudo famous painting. We have, of course, self-driving cars. We have voice recognition in various devices. We have heart rate monitors and actually cardiac events registering devices are getting more popular. Natural language processing is one of the ones that is growing fastest at the moment, as well as different technologies in image recognition. And really, there's a lot of hype and a lot of overpromise in the AI field in general. But I think, and many agree, is that image recognition is actually one of those fields where AI is currently optimally suited. There's really no other field where where AI has better power to actually change the way how we are doing things. And so there's a myriad of different neural networks out there, but if you really want to understand what's going on in classical image analysis for deep learning, you should look up deep convolutional neural network. So that's essentially all that our platform is based on. And so, depending on where your location is and what your background is with deep learning AI, this might be old news. But so you have to remember that it's essentially just a very complicated statistical model. So it learns from the material you're providing it. And necessarily, if just throwing a lot of data into an AI doesn't necessarily produce good results. There's a lot of failures that have used tons and tons of data. So you have to remember that quantity is not a quality of its own. You need to have good curated data, high quality data, and you need to have as little as possible label conflicts. Every time that you're trying to build a statistical model and you're showing examples of essentially the same thing, but you're calling it different, the AI will have a trouble have trouble actually generating the result that you want. AI will always find the difference between the items that you show it, and if you're showing it the same things, it will find the differences in noise. And of course, there are classical examples of this in academic literature where you have essentially trained it for something that you did not intend to train, just because the strongest signal was outside what you were thinking it was. Deep learning today is also partially a black box. So the AI model won't tell you why it's doing decision. It's making the decisions based on thousands, hundreds of thousands, or even millions of parameters. And there's a lot of debate about this black box. That is it bad to have a black box? And there's my take on it is that the more you understand of a process, that's obviously better. But we are using a lot of black boxes in the world, both in regular life and in healthcare. And as long as it's validated and it works okay and it's safe and has expected behavior, there's no reason to be afraid of the black box. And then also remember that AI doesn't solve all problems. You need to have a specific problem, and then you need to design the AI to solve that problem, and then you need to validate. And this is true. I'm assuming that everybody that's on this webinar is in research or somehow in science, and anyone knows that you never believe an assay unless you have positive and negative controls and you validate stuff. So for the data labels or data amounts that are required. I have an example of 3 images on the bottom of the that's different traffic situations. So let's say we are trying to make a self-driving car. You need to be able to drive in a roundabout in heavy traffic, but that doesn't necessarily tell you about what a road looks like in the middle of the desert. And training in the middle of the desert doesn't tell the car what the road looks like or what people look like when they are crossing the road somewhere in the northern Finland or in Alaska. So you have to provide the AI examples of all of these images, but providing millions of images of exactly the same example does not necessarily enrich the statistical model. Because when the AI has learned something, it has learned it, and then it just needs examples from other situations. And so while it has been really difficult to make self-driving cars, that's a field that is progressing quite quickly. But that's still an easy problem, because in healthcare, and especially when we are going into to clinical use digital pathology, you have to remember that human biology and pathology is much more complicated than any traffic pattern we can think of on the planet. So in reality, the AIs that we are training is actually more akin to Elon Musk shooting up a Tesla into Earth orbit. Those are the things those are the challenges that we are faced with. There is such a wealth of variability in the human body between individuals and within different locations of the body that it will be really hard to build a generalizable model that knows everything. So incremental advances where you are very certain about what the AI model is doing in a certain location for a certain intended use is definitely the way to go, both in research and in pathology. So one of the strengths of our platform is that we are agnostic. It does not matter where the image comes from, what acquisition form, what platform, is it immunofluorescence, is it bright field, is it radiology, it does not matter. If we don't already support that image format, we can provide that support rather quickly. And every once in a while, we have some projects where there's an image format or a device that we have not seen before, but obviously it's getting rarer and rarer. But when there is a new situation, we always work with you, and we will get you on board because we want you to be successful. So our mission is really making AI in pathology and image analysis simple. So what you need in order to get started, you need an internet browser, and you need to have your images, and you need to know what you're going to look for, or what your definition of, let's say, tumor is. So what you don't need a data scientist, you don't need a data engineer, you don't need to write code, you don't need to know Python, you don't need to buy hundreds of thousands of dollars worth of hardware, server racks, etc. And you don't need millions of labeled images. What you really need is anything that you have at hand. It can be solved. You can start big, you can start small, it does not matter. So I'm going to actually switch over here to showing you what the platform actually looks like. So this is a view that you get when you log in and you start an AI project. So this is actually a pre-created AI project that I've done just in the interest of time. So this is a tumor microarray spot, Ki-67, a staining of breast cancer sample. And the basis of our platform is really to do supervised learning. We also have the capability of do unsupervised learning, but for most image application analysis needs that you have, what you do is supervised learning. If you can supervise the learning, it's always better to do it. If you want to have emergent data coming out of it, looking for things that you don't quite understand in samples or trying to find new features, then you want to do unsupervised learning, and that's easy as well on this platform, but it takes a little bit more time and it takes a little bit more data. The process is more simple, it just requires more data. So we have two basic concepts. We have a training region, which is the black contour that I'm drawing. When you start the training for the neural network, the only thing the neural network or the AI is going to see is or the architecture is going to see is any pixel that is within these black contours that are here. And anything that is within the black contours will belong to one or two or more classes. So in this, we have two layers in this AI model. The first one layer contains only one class, which is epithelium, but in a hidden way, it also contains a second class, which is called background. So anything that's not annotated goes into background, which essentially, artifacts, things that you're not interested in. In this second layer, we actually have two different classes, plus obviously background. So in this case of epithelia, I'm going to draw my definition of epithelia. There's no right and wrong here. The AI is very neutral. It does not care what your ground truth is. Whatever you say is correct. And of course, that also means that you need to know what you're looking for. So on purpose, I'm discarding. I'm not going to count these couple of floaters that are out here on the side. I'm going to ignore them. And for me, epithelia is just these larger parts here. But I obviously also have some stroma here in the sample. And now I'm just erasing the annotation in order to define areas of stroma. I'm a little bit sloppy here, just in the interest of time. I'm just going to leave it like that. The interesting part is that, of course, when you do artificial intelligence or neural networks like we do, when you start running the analysis iteratively, you will actually be advised by the AI results where you have made mistakes. So you don't have to be overly cautious in the beginning. It's just start and get something in, and then you will see where there are data conflicts, and that will be easily pointed out to you. Then if you would like to train an object classifier, it's the same thing, a little bit simpler. You define a region, usually a smaller region than for doing those semantic that I just did. So now I'm gonna just mark, I'm using my mouse on a normal Mac laptop here. So I'm just denoting where I find negative cells. I'm gonna switch to the positive class, and there I have positive cells. So this is really anything that you need to do in order to build a classical Ki-67 scoring algorithm that first identifies epithelia, and then from epithelia counts positive and negative cells. When you train, you only need to do give it a name. You give it how many iterations you want to run. I'm going to do a quick one in the interest of time. And one of the new features that we have is that you can actually select which layers to train. When you do rather complicated model or you add on, if you already feel that your epithelia network is doing well, you can actually select a previous neural network that is going to use, and then you just train the nuclei model. So right now I'm just going to start all of these, and as you can see now, we uploaded the data, so it uploaded all the data in the black contours, and it ran and took 4 seconds for 20 iterations. Now 20 iterations is obviously not even close to enough to actually have a useful model, but it will tell you something. It will tell you, did you get anything at all? Object detectors are a little bit harder to train, and the semantic region identifications are easier. So verification has been completed, and verification is the inference. The new neural network is actually running inference on these training regions, and then you can sort according to where you made the highest amount of errors. And so the red contour here now is where the AI thinks that you have epithelia. So the dark red contour is the neural network, and the lighter pink is my annotation, the one that's surrounded by the dark solid outline. And so now here we have a couple of options. I can just retrain with more iterations or add more labels, but what I also can do is have the neural network help me define my ground truth. So if the neural network was smarter than I was, and I actually agree now that I see it with a second opinion, maybe that actually was not part of epithelia, and the neural network is actually better than I am. Then you can just quickly edit the annotations that you have, and then after you have gone through all of the examples here and made them more precise, either agreed with the neural network or then saying that the neural network is wrong. So here I feel that it's pretty solidly epithelia, so I'm not going to change that. And then you go through these, and then you run a new neural network after you have corrected the labels or added more labels, and you do a new run, and then you can, as an example, you can add 100 of these. So what are the things that we are able to achieve? So we are looking for, in many cases, you're looking for very fine structures and quantification. So this is an example of liver fibrosis, and it's nearly impossible to do this manually, and it's quite difficult for traditional image analysis methods. There are very few methods outside of deep learning that actually could learn how to differentiate between the pathological IHC stain and the normal physiological IHC stain that comes from the collagen, structural collagen that is around the portal veins. And we can also do spatial analysis. So from any object to any object, you can get distances, you can get sizes, etc. So you can get distributions of what things look like, and you can see if things are further or closer away between treatment and control in one of your examples, in one of your experiments. We have done quite advanced tumor grading for non-small cell lung cancer. So this is the KP mouse model collaboration with Tyler Jax's lab, and there's a previous webinar where Peter Westcott presented his data if you're interested, and you can follow up with Emma if you can't find the link and you want to know more. In that project we achieved pretty good agreement, especially on just total tumor burden between the human operators and algorithms. And then we have also advanced this, and this is actually something that was done in the lab of Tyler Jax at MIT, where they actually developed a IHC on the left. So this is a tumor profile, immunoprofiling IHC with three markers. And so what we are able to do with velocity is that we are actually able to take two different images. They can be the same image that has been restained and rescanned, or it can be serial images. In this case, it's restained and rescanned. So the image on the left is IHC that was done first. So it's an IHC for CD4, CD8, and Treg. And then after that, the section was processed again and stained with HC, and the image was captured again. So in this case, then we register the images to each other, and we do what we call tumor metrics. So I will again switch over to the live situation. It's a little bit easier to appreciate from here. So all of the things that I'm showing you that looks like a live browser here, all of this is used in the cloud. So I'm just sitting at my laptop and I have no fancy computational resources. I'm just using the regular cloud as any Aiforia user would use. So on the right hand side, we have one of the lobes of the tumor, and you can see there's a big tumor sitting here in the middle. This is a grade 1 tumor, so sorry, grade 3 tumor. So I'm just going to highlight that one, but there are some other tumor scores here as well. So that grade score now is dependent on the H&E slide. And so as you can see, the right hand side is synced with the left hand side. And then you can see that here on the IHC, you can see the immunohistochemistry. But it would be really hard to appreciate exactly what tumor grade, at least in a high throughput manner, what tumor grade just based on the IHC. But now with image match, you can actually use the AI overlay from the right-hand side H&E and get it superimposed on the tumor, on the slide for the IHC. And if we activate the object identification for these different immune cells, so these are object identification of CD4, CD8, and Tregs. So now one of the more interesting things in the IO field and space, of course, is that what happens with CD8 cells, so cytotoxic T cells, when you do a PD-L1 block or some other immune therapy. So do you actually get tumor killing activity? Usually when you have an immune block, CD8s are resident outside in the stroma or somewhere else in the tissue. They are not in the tumor. They can actually not attack the tumor. But then with treatment, you can get the CD8s to move into the tumor. And of course, then the important question when you do these kinds of research is to understand what is the distance of these CD8 cells to the actual tumor border. And now here you can, in an automated fashion, you can actually define the search distance. This one here, I think, was 200 microns. So any CD8 identified within 200 microns of a grade 3 tumor will now get recorded with both its location on the slide and its distance to the closest tumor border. So this is one of the coolest features that we brought out with Velocity, and it really revolutionizes how you can actually think and plan your experiments, because it does increase your potential for complexity and throughput quite drastically. So as I mentioned before, we are agnostic to different image modalities. Immunofluorescence works well, and is an example of a multiplex immunofluorescence where we have done essentially the same as in that previous slide, but here we are identifying the tumor, stroma, and necrosis based on the cytokeratin and other stains, and then we are measuring the distance within one slide instead of tumor match. It's a little bit hard to appreciate there on the right, but in the interest of time, I'll just not show that. We also have training to external ground truth, as I mentioned, and this is just one example where we have taken the same Ki-67 example that I showed you for the training, where we can train according to what the Ki-67 score is, either manual or quantitatively derived, and then we can train a regression model for the AI. That then can, on the right-hand side, you have prediction of what is the positivity of Ki-67 positivity in epithelia. And when we are validating this with manual scores, the concordance is extremely good. And then how quick and how easy it is to train with external ground truth really depends on how strong your data set is, what is the difference between treatment and control or different groups, what kind of complexity or problem you're looking for. I'm going to skip some of the examples that we have. If there's something that you see that is really interesting to your particular domain, please send us a comment in the question box and we can follow up with you. But so we do a lot in the neurology space. We can do motor neuron microglia. We have an interesting project together with Neuroscience Associates where we are analyzing a lot of different features on intact human brains over whole hemisphere being sectioned instead of slabbing and taking small pieces, so you can actually look at an intact section. We have malaria infection detection, so this is a typical example of rare object detection. And we have very comprehensive breast cancer scoring algorithms that we've done. But the interesting part here is that from a very complex and difficult image, you can find a lot of different things, and mitotic figures identifying different scoring based on nuclear size, etc. Is very valuable for drug R&D, and eventually and hopefully it will also have a positive outcome on healthcare or breast cancer patient outcomes. One of the things that we have talked about before is that we are democratizing because we are taking away the data scientist, the data engineer, and you can do your own work. But still, scientists and pathologists, you don't have endless hours to actually annotate your images. And so Velocity brings you something that we call image match. And so image match, quite simply, Annotation Assistant, forgetting my terminology. So Annotation Assistant, quite simply, is letting the AI suggest annotations for you. So you can do it both with objects and you can do it with region counters. So you can have, I will again switch stack to, so there we go. So this is now maybe a familiar picture. So this is a KP mouse model. So this one is a non-small cell lung cancer mouse model, has quite heavy tumor burden. And so in this algorithm, this is a very simple toy algorithm, quite easy for demos. I'm trying to identify what is tissue, I'm trying to identify what is tumor. So the way to do this is, of course, the same annotations that I did before. You do training, but then when you have done training and you want to speed things up, then you can just run Annotation Assistant. And now the actual AI will scan the slide for you, or all the slides, new slides in your data set, and suggest new annotations for you. So now the AI is asking you really that if it's this region, is this tumor or is it not? What is your definition of tumor? So it's saying that based on what you previously have showed it, it thinks this is tumor, but it's not 100% sure, and it would like to get your help. So our Annotation Assistant does not only help you provide labels fast, but it actually helps you provide the correct labels. So the Annotation Assistant actually looks for areas where it predicts that it will improve the most by your help. So even if you have to actually modify every once in a while the precise borders of what you think is tumor, it's very, very beneficial because you don't waste your time on annotating things that the AI already learned. And when you think that it's done, when you think that an annotation is okay, you simply just press accept. So in this case here, there's a lot of macrophages in here. So I'm a little bit unsure about this. So I'm going to say ignore because I don't want to take a stand on that. Here, the Annotation Assistant is saying that it thinks that this is actually background, this is not tumor, but it would like to have some verification for you. So you just click accept, and so on and so forth. You can also do this with objects, and it works in exactly the same way. You run Annotation Assistant on your object detector, like the KI67, positive, negative, and the Annotation Assistant will find you those objects and ask for verification. And when you have gone through this, you can quite quickly add labels. So there you see now there's a new label in my data set. So then when you have added a few of those labels, however much time you have before you need to log out and go home for a day or do rounds or anything like that, you just start a new training. And then when you come back, you can do a Annotation Assistant again. So it really speeds up. In our own internal work, we are very happy about using this because it reduces the development time drastically for those projects that we develop for external customers. One of the final things and I think that probably the most important thing that we have in Velocity is actually tools for you to do validation. Remember in the beginning I said that anything that is AI you need to validate, especially in science and in healthcare. It's just an assay, you need to validate. And so there's always a little bit of a difficulty of defining how you're going to validate, what are your actual scores, what are you measuring. And if you don't do pixel level validation, so exact agreement of exactly pixel on pixel, you will never know if your score is just correlating or if it's actually the same. Because on average, scientists, tend to agree a little bit on things. So if you're just looking for correlation, you'll find really, really good correlation. But if you're looking for how well the AI algorithm actually performs, you need to score on a pixel level, and we are providing that. So quite simply, you switch to the validation tab here. You invite your trusted validators. You just send them their email here. They don't need to be subscribers. They don't need to use be part of the project that you're using. You can use your colleagues. You can use somebody that is a specialist from across the world. They will get an email to get invited to your project for just validation. They will not see any of these other sheets. They will just see validation here. They won't see your training data. They won't see the analysis. So you can trust that they won't have bias. So they will just naively go and look for what they are seeing. Also, validators will not be able to see each other's validation. So if you invite 5 people, they will do independent scoring. It's only you and anybody that is part of this project that will actually be able to select the different the different validators that been invited. So here I've invited my colleagues Lindsay Smith and Bill Malloy, and actually a second account of mine. What you essentially do is that you define, as project leader, you define which areas you want to have validated by just drawing a region again. And then whenever the user logs in, I will get requested to go and validate on different regions. There. So now this is already a prior validation score that I've done. But so if you switch here between different people, you can see that Lindsay and Bill and me, we are not completely in agreement. So there is a difference of opinion here, and there's a difference opinion here. And when I said pixel level validation, so if you're just doing correlation and total area or something like that. So Bill had scored this as tumor, whereas I did not. And Bill did not score this area, but I did. But so these will partially cancel each other out. So the appearance of agreement is always higher if you don't do pixel level validation. And this is very important. And that is why we wanted to bring this tool to the user, so that you actually can know what the AI model that you have developed is doing. So in a nutshell, I've gone through a couple of different things. So there's really no matter what kind of algorithm you want to develop, what your image analysis problem is, what your image looks like, where it comes from, if it's bright field of view, fluorescence, or hyperspectral, or any other of many things. You don't need any data engineer, you don't need to write code or Python, you just need to read our quite simple help documents and get started. And of course, we have a help team that is there for you to get you started as well. And so we do provide services just as the software platform, and you can do everything on your own. Very agile, that's very nimble. You don't need to draw up statement of works, and of course, it's a little bit more affordable. If you have less time than you have resources, then you can of course do a statement of work with our professional team, and we can essentially design any AI model for you. We have done simple, we have done extremely complex ones, and we have delivered several hundreds of AI models to date. So there really isn't a problem that we cannot deal with. And if we don't have the subspecialty in pathology that is relevant for you, we will consult with you in order to understand your ground truth or find the specialty to provide those annotations. And so you will do your create annotations, you train the algorithm, you use active Annotation Assistant as a help. You can distill quite advanced metrics, you can serially register slide, and you can finally validate your AI model in order to publish or to submit for some kind of regulatory approval. And everything is just found under the same hood. So you really don't need to have a second data platform or second analysis platform. It's all baked in Aiforia Velocity. So with that, I'll stop, and I'll be very happy to answer all your questions. Please submit the questions in the panel, and Emma will be able to field those questions. And if we don't have time to answer all of them, we will follow up by email.
Great, thank you so much, Tom. So it looks like the first question we have is, how many images do you actually need to start training with Aiforia?
It's a great question, and it's an extremely difficult question. The smallest projects that I've been part of is essentially 20 whole slide images. That project was a very laborious task to quantitate everything within all of the slides. And just by training on a few of the slides, and actually only a small fraction, some few percent of those slides, you will be able to get an algorithm that actually can work on all of the slides. That algorithm would not necessarily generalize to external data sets, but the intended use for that was to quickly get a full quantitation of the slides at hand. Then in other cases, so the non-small cell lung cancer algorithm, the first version that was in active use, very productive and active use, was in the range of 100 whole slide images, and about the average annotation amount was a few percent of the total slide images. And of course, there you have to remember that there was the coverage on the annotation or the amount of annotation is needed because we are doing so many different classes, and also because there's a lot of slide and staining architecture variation in these samples. So in order to capture everything in these very difficult projects, you need to actually increase the slide amount. Then for clinical applications, that actually would be, be able to validate in a wide range of places and have extremely high level of robustness, you would have multiple hundreds, maybe 1,000 images. I think that's kind of the range that we're scoping out, but the amount that you have is the amount that you use. If it's low, then you need to be realistic about the performance. And if you have tons of data, then it's better to use more data. The only thing that can be said, of course, is that please use, if you have lots of data, lots of slides, use Annotation Assistant, because then you don't do labels that are unnecessary. Because just adding more of the same label does not really increase the performance of the algorithm. It needs to see a variety of your data set.
Great, thank you. So it looks like we have a couple of questions more. We should be able to get through them. So firstly, in regard to image match, can you do registration on serial sections?
Yes, so you can do registration of serial section, and you can actually determine what is the agreement of, because sometimes you have a little bit of distortion, or one section is cracked, or there's a tissue tear or something. So you can always get a percentage of agreement within the tissue sections for actually accepting the score. And that's something we have found that 90-ish% usually is suitable. Anything below that, you run into trouble, because then spatial metrics become very irrelevant, because there's too many disagreements on a whole slide basis. And also you have to remember that the further away the serial section is, because some sections are more serial than other. So if the cut distance is very, very short, then image match is super simple. If they are actually a long ways away from each other, then it becomes a little bit different.
Great. So it looks like we have time to answer one more question. And the question is, can Velocity or Aiforia really do any other training besides semantic segmentation?
Yeah, so semantic or region segmentation, object identification, and actually we are close to releasing also instance segmentation. So that will come out as well. But those are the ones that we are using.
Perfect. Great. Thanks so much for your time, Tom. So it looks like that's it for now. Thank you so much for everyone else's time. What we'll do is we'll send you the recorded webinar link after the webinar. And if you do have any questions based on Velocity or anything else, feel free to email us, or you can visit aiforia.com to book a demo and see any of these features or tools in action. So yeah, with that being said, we'll end the webinar. Thanks for everyone's time.